Hello, Yuma High School. Section 11.2, moving on with space figures. We're going to be talking about surface areas here, starting with prisms and cylinders. All right, so what's a prism, what's a cylinder? We're going to get into that, all the different parts, faces, lateral faces, altitude, height, lateral area, surface area, so etc. Both for prisms and for cylinders. Let's show you where we're at. A prism is a polyhedron with two congruent parallel faces, and these are called bases. Now, the other faces are all quadrilaterals, and they're called lateral faces. Now, our rectangular prism here, okay, we name a prism by the shape of the base. So here we got a rectangular prism. And that one's a little bit weird because any of these sides could be considered bases. All right? Just for simplicity, on this particular one, let's call this a base. That means this is parallel to the original base. The two bases are parallel. So the red makes the bases, and then in blue, these other four sides, the side, the front, this side, and the back, are all going to be lateral faces. A little easier to tell on these other figures. Okay, the bases here on the hexagonal pyramid, there and there, and then in blue we got 6 lateral faces here, here, here. 6 of them, you can see them all going around, okay? Lateral faces. On the trapezoidal prism here, the bases are arranged on the sides, okay? And the lateral faces are these ones around, going around here. Top, the back, the bottom, and the front side here, okay? So I know that's a little bit hard to tell, but I think you're getting the idea. Over here on the pentagonal prism, the bases are the top and the bottom with 5 lateral faces. And finally on the triangular prism there on the bottom, the bases are shown on the front and the back. Those are the parallel sides, and 3 lateral faces here on the bottom and over here, right? Okay, so we name a prism after the shape of its base, and no matter what, the altitude of a prism is still a perpendicular height from one base to the other. So that's got to be perpendicular, connecting the two bases. Same here. That would be our height or our altitude. Remember, it's not always going to be oriented up and down. Here our H is actually sideways. Here our H actually goes front to back. Okay. Sometimes we're going to have a picture drawn this way where they give us a little dotted line. Okay. The H is still going to be the parallel height or perpendicular height from one base to the other. Make sense? Okay, those are also called altitudes. All right. Now, if the angle between the base edges is 90 degrees, as it is here and here, and here, okay, that's 90 degrees going there and there. Okay, those are called right prisms. Okay, if those angles aren't 90 degrees, and it's tilted over, that's called an oblique prism. Okay, so these two are oblique, the other 3 are right, and for the problems in our book, you can always assume that a prism is right unless the problem tells you otherwise. Okay, notice also that lateral faces of a right prism are always going to be rectangles. All of these shapes have to be rectangular. Okay, for a right prism. Not so with an oblique prism. We will have some faces that have to be parallelograms. Okay, not necessarily all of them. For example, this could still be a rectangle here, but not every face will be a rectangle as it is on a right prism. Got it? Got it. When we talk about surface area of a prism, we do this by adding all the areas of all the faces. Okay, so the entire surface, in this case I've got 8 faces, I would have to take all 8 surfaces, top, bottom, and 6 lateral faces, and calculate the area for all of them to get the surface area of the whole prism. Now, one way we can do that is by drawing a net. All right? So, for this particular figure, you can see the net folds out this way. We have 2 bases, one on the top, one on the bottom, and 6 lateral faces. Okay, so we can calculate the area of the 2 bases and each of the 6 faces, add them up, and we have the surface area. So for the 2 bases, we'll do it just like we did throughout Chapter 10. We're going to calculate the area of the hexagon by looking at the little triangle that we formed there, and using our tangent of 30 to find the apothem, using the formula apothem equals 1/2 of, or area equals 1/2 of apothem times perimeter, and we find that the area of one base is 259.8. Okay, so you can follow the math there if you need to slow down and check on that again. Now, each of these 6 lateral faces is 10 by 20 for an area of 200. So we add up the 2 bases, so 2 times the area of one base, and the 6 lateral faces, each of them being 200, and we get 1719.6 centimeters squared. So that's one way of doing it. Let me show you another way. Okay, notice, and this is going to come up often, okay, the surface area for this figure is going to be 2 bases plus the lateral area. LA stands for lateral area. Okay, now we can notice that the lateral area, instead of just writing the 110, I wrote all of these as being 10, 10, 10, 10, 10. Okay, if this is a regular hexagon, which we've been assuming, we'll notice that this adds up to 60. So we can consider the area of all the lateral faces as being one big old rectangle, right? That's 60 by 20. Okay? Now, notice that that 60 happens to match perfectly with each side of the base. In other words, that 60 is the perimeter of the base. Okay? And therefore the area of the lateral faces is a rectangle that's the perimeter of the base times the height of the prism. So we can take this 2b plus LA and look at it as being the same as 2b plus perimeter of the base times the height of the prism. Gives us 2 ways to look at this problem. Surface area is still 2b plus the lateral area, but the lateral area doesn't necessarily have to be calculated by 6 individual faces. It can be calculated now by using perimeter times height. Perimeter of the base times the height. So let me show you how that works. We're going to do an example here, and we'll do it both ways. Okay, so pause, do it yourself if you want, but here comes the way it goes. Okay, so find the surface area of this prism. First thing I need is the area of the triangle. Okay, so the area of the base, B, we need to find the height of the triangle. Okay, yeah, I showed it to you right there. Here's the net. Okay, so the height of the triangle is X. We split it into 2 smaller triangles. So we look at this 3 and a 5 hypotenuse, knowing that's a right angle there. We find out using the Pythagorean theorem that height has to, or that X, height of the triangle, has to be 4. Okay, so one base, using 1/2 base times height, the formula for a triangle, is 1/2 of the 6-inch base, 6 centimeter base, 4 centimeter height, and one base then must equal 12. Okay, then we look at each of these faces, the lateral faces. 5 times 12 is 60. 6 times 12 is 72. 5 times 12 is 60. So we add up all the areas. This is 12. This is also 12. And we add them all up. 2 12s plus a 60 and a 72 and a 60 gives us 216. Cool? Cool. So that's one way to do it. Here's the other way. Same figure, using same area for the triangle, but now we're going to use surface area equals 2b plus pH. I can put in the 2 times 12 for the bases. The perimeter is 5 plus 5 plus 6, or 16. The height is 12, and we still get our 216 centimeters. Okay, so that pH thing works kind of handy. Now let's jump over to cylinders, because they're really, really similar. A cylinder, though, is a solid with 2 congruent parallel bases, but the bases now are circles. Okay, so here's a bunch of examples. Once again, they can be right. That's a right angle. They can be oblique if it's not a right angle. So I got a couple oblique ones here, and the rest of these are right. Okay, and again, in our studies, you can assume that the cylinder is right unless the problem tells you otherwise. So when we talk about surface area for cylinders, let's look at the net. I want you first of all to look at this circle. Has a circumference, the distance around it, that perfectly matches the length of the lateral face. When we unwrap it, it's like we're cutting that lateral face in half and unwrapping it around to form a straight surface here. And you might remember this from chapter 1 also. The net for a cylinder looks like this for a right cylinder. Okay, so putting some numbers on it, if we look at our cylinder, it's got a radius of r and a height of h. And as we unwrap the side, that r becomes the width of our rectangle, and it is also, remember, the same as the circumference of the base of the circle, which is 2 pi r. So we again take our surface area, which is 2 bases plus the lateral area, but now we know that the area of the base is pi r squared, and we have 2 of them, and the area of the lateral face is the circumference times the height to make this rectangle, or 2 pi r h. So really handy way of doing surface area for cylinders is to remember that formula there. An important consideration, and I'll stress this again many times, is that there are a lot of problems we're going to do that don't need both parts. Some problems we're not going to use, say, for example, one of the bases, so we'll only use one part there. Okay? Other problems, we're not going to use either of the bases, and I'll give you an example of that later. So this goes away entirely, and we only use the lateral area. But let's look at some examples on that. Okay, just I need to stress that notice that the formula comes apart, and sometimes we're not going to use all 3 of those parts. All right? Here's one where we will. Surface area of the whole cylinder. Leave your answer in terms of pi. Nice and simple. Surface area equals 2 bases plus the lateral area. Bases are pi r squared. Lateral area is pi r 8 or 2 pi r h. Plug in the numbers using 6 for radius, 15 for height, and we find our surface area is 72 pi plus 180 pi, or 252 pi. Okay, again, stressing we don't always use every part. For example, a kindergarten class may be doing an art project using toilet paper rolls covered with crepe paper. Now the rolls are 6 inches high, have a 1-inch diameter. What's the area they need to cover if they're wrapping just the outside of the roll with crepe paper? Well, we're not covering the ends of the roll. We only need crepe paper to cover the lateral area. So we're only going to use that LA part and ignore the 2B part. So the surface area that has to be covered is just 2 pi RH. And we plug in the values and get our answer 37.7. And that should get us going.